Hello viewers, you are welcome to this video. We are going to use the method of Laplace transform to obtain the solution of this second order ordinary differential equation. And as you can see here, we can refer to this problem as initial value problem. Why? Because when x is 0, we know that our y is 4 and the y dx is 9. That is why we can refer to it as initial value problem. Just like I've explained to you in the class that the first step we need to do is to find the Laplace transform of both sides. And as you can see here, we have second derivative, we have first derivative, and we have y, which is the dependent variable we are looking for, and we have 0 on the other side. But remember that this problem is also known as a homogeneous problem, because you can see that the left hand side is equals to 0. So when we find Laplace transform of both sides, so for the first one, we have the Laplace transform of second derivative, which is x squared L of y. In the physical classroom, L of y here, you can remember that I call it x of x. Okay, it doesn't mean anything, just be very conscious of that, because that is what we are looking for. That is the Laplace transform of the dependent variable. So, and then for the first derivative, we can see that we're having 5 multiplied by the Laplace transform, and then Laplace transform of y, we have it there. But remember that the next thing now is that we must substitute the condition. Here we have 2 conditions because we are dealing with second order. So the first one is y of 0 is 4 and y prime at 0 is what? Is 9. So if you look at this now, after we substitute our initial conditions, which are the 2 initial conditions, we can see the next thing now. So we need to simplify it, because 2 we expand all the 2 we multiply the Laplace transform of second derivative, including the conditions. So we have that one. Then the next thing, as I've explained in the physical classroom, is that we need to rearrange and make Laplace transform of y the subject of formula, and that will give us the partial fraction. It gives us a fraction. You give us a fraction, and you can see here now that by the time you make L of y the subject of formula, we are definitely going to see a fraction. A fraction must emerge. So when we see the fraction, the next thing is for us to find the Laplace inverse of both sides, because Laplace inverse of the first side will give us y, which is the dependent variable we are looking for, and the next one is Laplace inverse of x, 8x plus 38 over 2x squared plus 5x minus 3. So now let's undo this partial fraction, which I think you can all do that perfectly based on our physical classroom. So as usual, you can see now that here we have 2 escape routes. The first one is when x is equals to minus 3, and the second one is when x is equals to 1 over 2. So that will help us to find a and b, and as you can see here, our a is 12 and our b is minus 2. But remember, this special fraction here is belongs to what? To the first category, because you can see that the denominator can be expressed in a linear form. Okay, definitely you can see that. So by the time we resolve the partial fraction, then we can now see clearly now that our solution, which we are looking for, is the same thing as Laplace inverse of 12 over 2 into bracket x minus half, then minus Laplace inverse of 2 over x plus 3, which gives us 6 exponential half x minus 2 exponential minus 3x. But the point here is that we are able to find the Laplace inverse because we're able to use the partial fraction perfectly and accurately. So I encourage you, please take your time to do revision on how to break down any big fraction. There are 4 categories, just like I've mentioned in the physical classroom. There are 4 different categories, and you should be able to understand how to handle each of them. And at the same time, remember, if you want to jump, please try to be very smart about that. Thank you very much for watching. Bye.